Thank you for coming. This talk is the next frontier in open source Java compilers, which is just-in-time or JIT compilation as a service. My name is Rich Hagarty. I'm a developer advocate from IBM, and I'm happy to be joined today by Marius Pirvu, who's a senior software developer who's a major contributor to the technology we're going to be discussing today. So we're basically going to talk about JIT as a service, what it is, and an implementation of it that's currently available. We're going to go through some graphs showing you how it compares, and we're going to have hopefully a demo, how to use it, and some recommendations. So let's do a little JVM primer. I'm sure this is all old news to you guys, but we'll go through it. Basically, you compile your Java code into bytecode, which is passed to the JVM for execution, the Java virtual machine. Its job is to load it, verify it, and pass it to the interpreter, which runs it 1 byte at a time. And we all know this is relatively slow. So the JIT, or the just-in-time compiler, helps out. There we go. It actually compiles the code into optimized machine code. And it doesn't compile everything, just the hot methods. Those are the methods that are repeatedly called. It does have a code cache, so that for the lifetime of the JVM, those are stored. And of course, it's going to run 10 times faster than the interpreter will. And that Java code, the JIT compiled code is very optimized, and the longer your JVM runs, the more optimized it'll be. And the reason it can be so optimized is running in the actual runtime of your application. So that's good, but also has some negative effects. There are some disadvantages. Namely, that it's sharing CPU and memory with your application. And this mostly affects startup and ramp up of your application. So real quick, startup time is the time it takes your application to be ready to accept requests. And ramp up is that additional time it takes to become optimized. So all the methods that need to be compiled will be compiled. And this mostly affects your application at startup time, because that's when most JIT compilations occur. And it gets worse in a container environment where you have less and less resources. Here's an example of a graph of what happens with the CPU. You can see the spikes occurring initially at the start here. That's when all the JIT compilations are occurring, but they can happen during the life cycle of your JVM. And anytime you have those spikes, it does affect the quality of service of your application. Associated with that is memory usage. These are spikes in memory usage at the beginning here. And of course, whenever you have spikes in your memory, that can create out-of-memory events, which in the best case is just a hiccup or lower quality of service, but it can bring down your JVM. So that's the number one reason why JVMs do fail, is because of out-of-memory events. So how do you get around this? Well, if you have lots of money, you can just over-provision all your applications, right? You can build in enough memory that it can handle any of those spikes. But if you're trying to manage that, you're going to try to get that window down as small as possible, but it's very hard to do. Java in itself is very undeterministic with its behavior. You can run it again and again, and you can get little different spikes in different places. So it takes a lot of experimentation and tests to figure out exactly how much you need. So it's a very hard job, hard undertaking. So a solution to this problem. So we like the JIT. It produces very optimized code, but it has some disadvantages. So how do we handle this? A solution could be, in concept, JIT as a service. And so what we're talking about here is, in this case, we have our application JVMs running here, and we have remote JITs running as services on the cloud. And requests for compilations will be sent to our remote JITs. So we're showing this as a cloud services. So we get all the benefits of, for example, Kubernetes. So we get auto-managed by that. So it ensures our availability, reliability, and scalability. This solution is very much like the trend of going mono to micro. So in this case, our monolith is the JVM itself, and now we're splitting that up into two lightly coupled microservices, one being the JIT and the other being whatever's left in the JVM. And of course, it's resilient because we show the JIT being crossed out here, but if these become unavailable, we still have access to that local JIT, so we run like nothing happened. So there is an actual implementation of this, and it currently exists in the OpenJ9 JVM, and it's called the JITServer. Its actual branded name is the Xamaru Cloud Compiler, and I'll talk a little bit about why it's called Xamaru in a minute. But OpenJ9 combines with OpenJDK to form a full JDK. Everyone understands that. I think everyone knows about that. So it's free to use, free to download. And of course, here's the GitHub repository for it. Little background on the OpenJ9. First of all, has everyone heard of the OpenJ9? I think everyone here, yes. So it started life about 25 years ago as the J9 JVM, started by IBM. And the reason they came up with it was because they wanted to make sure that all the Java workloads can work on all of their devices, all the way from handheld scanners to mainframes. So in order to ensure that, they had to build their own JVM. And about 5 years ago, they open sourced it to the Eclipse Foundation, rebranded it to OpenJ9. And of course, it works in all environments, so it goes from small to large. It can handle very constrained environments, all the way up to the mainframes. It is known for its small footprint, fast startup, and ramp-up time. And of course, all the large Fortune 500 companies run their enterprise software on OpenJ9. So it has a long history of success. So it's called the Xamaru Cloud Compiler because the distribution is a part of IBM's Xamaru runtimes. So this Xamaru runtimes is basically IBM's distribution of the OpenJDK. And it comes with the OpenJ9 JVM. In fact, it's the only distribution that does. And of course, it's from IBM. Like most the high-end vendors, we're going to, it's available for no cost, high performance, all the good things you're looking for. It comes in 2 editions, open and certified. The only difference is licensing and the platforms that are supported. It's available. There's the IBM.biz link, Get Xamaru. You can get free downloads of this. It's also available in the Adoptium marketplace. So Adoptium is the keeper of the OpenJDK binaries, and they have a marketplace where all the major vendors have links to their downloads, and IBM Xamaru Runtimes is a part of that. If you're going to run it as a container, you're going to need the image. So it's available in Docker Hub, IBM Container, and Red Hat registries. So let's talk a little bit about the technology itself. From the perspective of the client accessing this new JITServer or Xamaru Cloud Compiler, so for provisioning, it's a lot easier. We just worry about the application now. We don't have to worry about the spikes or handling these, what the JIT compiler is going to take from us. You're going to get improved ramp-up time, again, because all the resources are going to be used by the application. And in fact, the JITServer or the Xamaru Cloud Compiler is going to be helping us at initial startup because it's going to be doing all of our JIT compiles for us. The reduced memory consumption means in a container world, we can size our containers down and we can fit more onto a node. And I think this is probably the sweet spot for this technology. And resiliency, we showed this earlier. If the compilers, they're unavailable, they could become unreachable, we have our own local JIT in the JVM still. And it's available on these systems here, architectures. It supports Java 8, 11, and 17, and it works wherever OpenJ9 works. In fact, the JITServer is basically another OpenJ9 JVM just running under a different persona. It does have a dependency on OpenSSL, only for encryption, which I think you'll talk about here in a minute. So with that, I'm going to turn it over to Marius and talk about how it performs.
Yeah, let's see some performance graphs. First, we'll show you how JITServer can improve cost when running Java applications in the cloud. And for this experiment, we use ROSA, and this stands for Red Hat OpenShift Service on AWS. We used the Amazon cloud to prove that this technology is not tightly connected to IBM hardware or software. It can work with any cloud provider. In our experiments, we use 4 applications, and these are Acme Air microservices, Acme Air monolithic, so 2 versions of the same application. Acme Air is a Java EE application that runs on top of OpenLiberty and implements an airline reservation system. We also have the renowned Pet Clinic benchmark from the Spring Boot framework, and we also use a small Quarkus application. And we are going to apply a relatively low amount of load in order to simulate conditions seen in practice. Now, this is a busy slide, so please bear with me. You see many boxes, color boxes here, so those are containers. So each color represents a different application or a different service. There are some numbers in each container, and that represents the amount of memory, the limit for those containers. We actually run many experiments to determine the minimum amount of memory that an application needs to run without an out-of-memory event, and we set that value as the memory limit for those containers. So let's take an example. What is this here? So let's it's the other way around. B550 represents the booking service, and it has a memory limit of 550 megabytes. These boxes were drawn at scale. This means that a bigger box is a container that uses a bigger memory limit. So even at a glance, you can see that the containers for the top row, which represents the default configuration, cannot simply fit into just 2 nodes. You need 3 nodes to accommodate them. Whereas with the JITServer configuration, which is at the bottom, you can cram all those instances onto just 2 nodes, even after you account for the memory taken by the JITServer instances, which you can see there in that shade of orange. Overall, the JITServer configuration takes 6.3 gigabytes less of memory and uses 2 nodes as opposed to 3 nodes. Therefore, we realize savings of 33%. But cost savings is not the entire story, because if the throughput is bad, then you may not want to use JITServer. So let's have a look at the throughput. So this slide shows the throughput for the 4 applications that we use. And the important thing to notice here is that the throughput for the JITServer configuration at steady state is exactly the same as the throughput for the baseline configuration. So the takeaway from these experiments is that JITServer can effectively improve container density and therefore reduce the cost of running Java applications in the cloud anywhere between 20 to 30%, while delivering the same amount of throughput as the baseline. Therefore, the important metric throughput per dollar is improved by JITServer. Now let's see how JITServer can improve auto-scaling. You probably know that Kubernetes has a horizontal pod autoscaler mechanism. And this one measures a certain metric, and typically it's the CPU utilization. When that metric exceeds a certain threshold, it's going to load or trigger new pods into the system in order to take on the load. Now, I configured the autoscaler here to launch new pods when the average CPU utilization per pod exceeds 0.5 CPUs. The pods are limited otherwise to 1 vCPU. The graph on the left shows the throughput of the Acme Air application while we apply an increasing amount of load to it. As you can see, the throughput for the JITServer configuration is always better than the throughput for the default configuration. So you compare the line in blue, JITServer, with the line in orange, which is the default, the baseline. So why is that? Well, Java is known for needing some time to ramp up because it needs to compile all those methods. With JITServer, you can accelerate the ramp-up time of application, and therefore your application now responds faster to increases in load. And there is a secondary reason here. So let's say that you don't use JITServer. When the autoscaler brings a new pod, then this pod is going to cause a flurry of compilations which are going to consume CPU. And now the autoscaler may misinterpret this extra CPU as load, where in fact it isn't. So the autoscaler will bring new pods into the system, thinking that is going to address the load. And later on, when those compilations subside, is going to realize, hey, situation is not that bad, and is going to delete some of the pods. So therefore, with JITServer, we can eliminate this bad effect on autoscaler. Now let's go through a demo. But before doing that, I'm going to explain the entire setup that we have here. So the goal of this demo is to show you that JITServer can effectively improve ramp up of Java applications, and it can do so with a smaller amount of memory. So we are going to use 3 Acme Air containers, these 3 here. The one at the top is limited to 400 megabytes of memory. The one in the middle is limited to 200 megabytes, while the one at the bottom is still 200, but it also receives help from JITServer, meaning that it can offload compilations to this JITServer instance here. We apply load with 3 JMeter containers, and the throughput values are communicated to InfluxDB and from there to Grafana in order to be displayed as graphs. We also have a Prometheus container which scrapes performance metrics from JITServer and then displays them in Grafana. And now I'll have to get out of presentation mode and start the demo. So I have created some scripts so that everything goes smoother. It does not show up because I need to be. Okay, now I need to kill this. It's extended mode. It should be in. Duplicate. That should be better.
That's better.
Yeah, now they should be displaying. Okay, so I'll have to start MongoDB first. Then I'll start JITServer. I'll start Prometheus. Everything runs in container here. Then I'll have to start the 3 Acme Air instances. So let's have a look inside this script to see what it does. So as you can see, there are 3 Docker run commands in here for launching the 3 containers, and they are all very similar, except that the first one is limited to 400 megabytes, the second one to 200 megabytes, and the third one also to 200 megabytes, but it also receives some extra options to transform this OpenJ9 JDK into a client. And we do this by using these options, XX plus use JITServer, and then you specify the JITServer address and port. Now let's have a quick peek into the script that applies load, which is this guy. So we apply load with the 3 JMeter instances. Again, we have 3 Docker run commands, and they are very, very similar, except that they use different ports. So now I'm going to apply load. And we are going to Grafana dashboard. I have to maximize the screen. It's going to take some time for the lines to appear, but let me describe what you're going to see here. So on the top left, we have the Acme Air configuration that uses 400 megabytes of memory. On the right, we have the configuration with just 200 megabytes of memory, while at the bottom, we have the Acme Air that receives help from JITServer and also uses only 200 megabytes of memory. So the goal here is to show that it can ramp up faster, and while it may need some time to reach peak throughput, you can clearly see that the JITServer configuration is achieving higher amounts of throughput in a faster manner than the other one. Let's talk about this configuration with Acme Air 200 megabytes. So this is running vanilla OpenJ9. The throughput is quite low, and in most of my experiments, it doesn't exceed 1,000 operations per second. That's about half of what the other guys is going to achieve. This is because 200 megabytes is really not enough for the application threads and the compilation threads to work in such a limited space. And our JIT compiler would rather fail some compilations rather than risking an out-of-memory event. That's why, because of the many failed compilations, the throughput of this instance is going to stay low. Going back on the left, the JITServer instance has reached peak throughput, which is about 2.5 thousand operations per second. And the vanilla OpenJ9 is right now getting there. So definitely better ramp up with JITServer than with vanilla OpenJ9. And again, we use half the memory. So half the memory, but way better throughput with JITServer. And now let's have a look at some metrics that are collected by Prometheus. So JITServer can export 4 performance metrics, custom performance metrics. And those are the number of connected clients on this panel. In this case, we only have 1 connected client. On the right, at the top, we have the CPU utilization. You see there is a big spike in CPU utilization because CPU compilations, JIT compilations require CPU in order to be performed. At the bottom, aligned with this, is the available memory at the JITServer. There is a dip here, again, because JIT compilations need memory in order to be performed. Whereas on the left, at the bottom, we have the number of compilation threads. So at some point, we compiled in parallel on 5 compilation threads, and then the number of compilation threads goes back because compilations have subsided. Okay, so that's all for my demo. I need to get out of here and get back to the presentation. Okay, so now let's see how easy it is for somebody to use JITServer. It's important to note that JITServer is an intrinsic part of OpenJ9. It's not a separate technology. So basically, you have OpenJ9 operating in 3 different personas, depending on how you invoke it. If you invoke it as Java and then my application, then it's going to act as your regular JDK. However, if you use the JITServer launcher, then OpenJ9 is going to act in server mode, where it's going to wait for compilation requests from a client. And finally, if you provide this XX plus use JITServer option, then OpenJ9 is going to act in client mode, where it's going to offload compilations to a third-party server. Where is that server? Where you can specify the address with the XX JITServer address option. This one here. And we have many other options to configure JITServer. A full list can be obtained from this link that I put here on the slide. So how about in Kubernetes? Well, again, it's very simple to use it in Kubernetes. Typically, you need to create a deployment and a service. You can easily do so with YAML files, or you can use Helm charts. I put here the link for the JITServer Helm chart repository, or you can use operators. Right now, we don't have operators, but we are working on it, and they will be available shortly. At the bottom of the slide, there is a link for a very good tutorial on how to deploy JITServer in Kubernetes using YAML files and Helm charts. You can definitely encrypt the network communication between the client and the server and ensure trust by using TLS. All you have to do is provide the file with the certificate and the file with the private key by specifying the options that you see here in blue. So these files can be stored into as a Kubernetes TLS secrets, and then made available to the containers through volumes. And this is just one example on how you can do this. There are many other options. In terms of monitoring, I've already shown you that you can connect Prometheus to monitor performance of JITServer. Right now, we only offer 4 custom metrics, but if we find the need, we can easily add some more. We also have an extensive verbose logging mechanism. For instance, I find this option XX JITServer log connections very useful because when you use it, there will be a line appearing in the verbose log when a client connects to a server. So this is an immediate indication that the connection has happened. So let's go through some recommendations. When should you try JITServer? So I would say you should give it a chance when the fight between the application threads and the compilation threads is more fierce. And that can happen when your application needs to compile many methods in a short amount of time. Or it can happen when your application is constrained either in memory or in CPU. You probably want to ensure that the network latency is as low as possible. 1 millisecond, it's a good network latency to have, and this is easily achievable in modern data centers. I would connect anywhere between 10 to 20 JVMs to a single JITServer instance. You can go more than that. We've connected more than 100 with no problem, but in those cases, you need to give JITServer more memory and more CPU. Speaking of memory, the JITServer uses between 1 and 2 gigabytes of memory. You may achieve better performance if the compilation phases from different JVM do not completely overlap. So try to start your application in a staggered manner. Encryption does add to the overhead, anywhere between 5 to 10% extra CPU. So if you can avoid it, yeah, please do so. An important point, in Kubernetes, you must use session affinity in order to keep a client connected to the same server. If you let the client switch to another server, then you cannot take advantage of the caches that the server has built inside, so you may lose some performance. And finally, if you want to improve CPU utilization across the entire cluster, you could use this optional mechanism, which is called JITServer AOT cache. So what happens with this mechanism, the methods that the JITServer has compiled will be stored locally. And if another client wants to use a method that has been previously compiled, then it can be fetched directly from the JITServer cache rather than compiling it again. So you save on CPU for compilation. It sounds simple, but trust me, the implementation is very complicated. So to conclude, what have we learned in this presentation? Well, JITServer is very good for improving throughput of applications, but it adds overhead. And one solution to mitigate this problem is to disaggregate the JIT from the JVM. And in order to do so, we can use a JIT compilation as a service solution. We have implemented such a solution in Eclipse OpenJ9. It's called JITServer. It also goes by the name of Semaru Cloud Compiler. It's available right now on Linux for Java 8, 11, and 17. And it's especially good for constrained environments, so think microcontainers. It's Kubernetes ready, and it gives you a lot of performance benefit. It can improve ramp up, auto-scaling, performance of short-lived applications. It can reduce your peak memory footprint and increase application density and reduce cost of Java applications running in the cloud. That concludes our presentation. Final slide for resources.
Yeah, so everything that we talked about here is available on these links. I would suggest, let's see, on the next page, I think I added, so you can get these slides here. That's probably the best way to do it. And you can always get a hold of me here. We'll take any questions you have now, but we'll also be at the IBM booth, which is right out front here by the, we'll be there the rest of the day.
Yes.
Go ahead.
Do you think that it should be possible to create some kind of Lambda runtime in AWS that is able to exploit the media available compile server, so I can attach several Lambda functions to this compile server in order to make a startup faster for the Lambda functions?
So if I translate your question, can we use JITServer with Lambdas?
Yes, okay.
Okay, and the answer is yes, as long as you have a JVM that has a JIT and you need to offload that, yes, you can use it.
But
So for Lambdas, startup is also important. JITServer may help with startup, but there is another technology that we are working on that is going to help you with startup even more. So that is the instant on. There was a talk about this. So with instant on, it uses the CRIU technology in Linux. And what happens, you checkpoint your application after startup. You create a Docker image with that. And then you start like in milliseconds instead of seconds when you restore.
Right, and I think that's in beta right now.
It's in beta right now,
Yeah.
yeah. And yeah. So these two technologies, like Instant On that I talked about, and JITServer can work very well together because Instant On is going to help you with startup, whereas JITServer can help you with ramp up when, after the application starts.
Oh, yeah, the problem with the resources line, some of these are just, the links are hyperlinks, so you really don't know how to get there.
A question right there.
Architectures, is this available? I'm specifically asking for ARM, because you, for instance, the new Macs, or I think in the server, ARM might also play a role, so I was wondering if it's only x86 or it's also something different.
Okay, so the question is if we have JITServer for ARM. We target ARM. We don't have it at the moment, but it is on our mind. I cannot tell you exactly when that will happen, but yes, that's next in terms of platforms that we want to support. ARM is next.
I was wondering because I looked at OpenJ9 and there's a ticket from 2017 requesting ARM support. So.
Yeah, we are resource constrained. Any other question? Yes?
So does the JITServer and the client have to be the exactly same?
They have to be the same OpenJ9 release, and yes, you must use the same Java version, meaning you cannot mix Java 8 with Java 11. They have to be same J9 open release. That's the concept. The story is more complicated, so there is a version for the JITServer itself, and only that one has to match. But because it's still under active development, JITServer changes enough such that if you move to another OpenJ9 release, the JITServer release is also going to change. And therefore, at the moment, yeah, it's probably one-to-one, release to release. In the future, it may be more stable, and therefore, this matching of OpenJ9 release may not be true anymore. Yes. Oh, sorry.
For the communication between the client and the JITServer, is this like just does the client do one request and get back the results?
Very good question. No. Yeah, that's ideal. So the question was, is there just a request-reply kind of traffic for the JIT compilations done remotely? And the answer is no, because the server needs to know many pieces of information about the classes, profiling information, and so on and so on. So typically, or on average, we see like 50 messages being exchanged per compilation. Of course, if you use the JITServer AOT cache, it's just one round trip because you just take the method from the cache. But yeah.
Maybe just a quick follow-on question. So how does the JIT cache work? Like if one client compiles a method and the second one wants to compile the same method, it's not clear if
No,
the same profile. So
you're talking about two different clients compiling the same method or not the same method?
the same method, because only then you use AOT cache.
Yes.
Yes. But the two clients may have different workloads, but compile the same method. Then the profile
Yes. Yes. So in that case, if you have two clients connecting or running different applications, but they so happen that they use the exact same method, the profiling information for that method could be different. And in that case, you may lose a little bit of performance penalty. However, we target mostly the cases where you work in Kubernetes and you have, like 10, 20, or even more instances of the same application because it's replicated so many times, and therefore it's the same application requesting the same method from the JITServer. Yes, another question?
It's a bit along the line of that one, I guess. You have this picture where there are many applications on one server, and one JITServer. So required that these applications share the same, say, libraries with the same versions, because otherwise, say, if I have one method from this library to be compiled or to be optimized, it might clash somehow with another one. So would it be preferable to have, say, all the dependencies and versions of libraries in the same version so that the methods are the same?
I couldn't quite get the question. Is it about the versioning that you need to?
So you have these different colors.
Yes.
Applications. So these applications have dependencies. So if I have, say, one's a library in version A and one the same library but in version B, the information about these libraries when they're optimized might be different.
Yeah, it's up to the person that deploys to say, well, is it?
I think the question is about how you decide if two methods are the same. I think it's not done just by name, but you have some checks.
So you are talking about the fact that two methods with the same name may actually refer to different codes because they have different versions. Okay, yes. So in order to ensure correctness, we have a cryptographic hash for the method, so we make sure that that is the right method to call.
But then you still have like two methods to be cached, and so if they would be the same,
yes,
then you would have only one which would be say.
That is correct. Yeah, yeah. So right now you cannot store the same method twice. I mean the same method name but different code. But in the future we may want to add that as an extension. Yes. So you may hold the same method but different compiled bodies for different applications.
And maybe the other way around. They are like two different methods. I have to cache it twice because one for version A and one for version B. And so if I try also to align all the applications to use the same dependency versions, then for different applications I will still have to cache only once. That was my assumption.
Yes. We can take this. We can debate this on the booth because it gets very technical at some point. Yeah.
I think that's it. Thank you very much.
Thank you.